Hi, my name is Patrick Reagan. The Computer Primary Component series will go in depth of the individual components that make up the computer. The first video, CPUs, discusses processor characteristics and architecture, including processor speeds, multi-core processing, pipelines, buses, and cache. It also discusses simultaneous multithreading and virtualization. At the center of the computer, logically speaking, is the microprocessor, sometimes referred to as just processor, central processing unit, or CPU. Everything is built around the microprocessor, which is usually a single integrated circuit or chip. It can retrieve instructions and data, do mathematical calculations and comparisons, logical decision making, and output the results. Because of this, many think of it as the brain of the computer. The processor is plugged into the motherboard. The processor will follow instructions provided from memory and perform the computer tasks specified in the program. It will communicate with all peripherals over the system bus. It controls the sequence of instructions and the flow of data from one component to the other. The registers are small memory spaces in the processor to temporarily store instructions so that they can be executed and store data so that it can be manipulated. Registers are normally measured by the number of bits they can hold, such as 8-bit registers, 32-bit registers, 64-bit registers, and 128-bit registers. Larger registers can handle larger numbers and more precise numbers, or more decimal points in one action. Larger registers can process multiple smaller numbers during the same action so that it does more in one action. However, software has to be written and/or compiled with a modern compiler that can take advantage of these actions. While smaller registers can still process larger numbers, it may require additional actions to complete. For example, you may have two registers called AX and BX. Step 1, you first move the number 3 into AX, and then step 2, move the number 5 to BX. Of course, the 3 and 5 are written in binary number consisting of on and off signals. Now that the two numbers are in the CPU, step 3, you can perform a bitwise function that adds the numbers together. We all know that 3 plus 5 is 8. Of course, the 8 will be represented by a binary number. Step 4, you can store the results in another register so that it can be used for something else, or you can also save it to memory or RAM, or output the number to a device such as a monitor or printer. The processor is a busy data processing factory. To keep it busy as possible and working hard, a pipeline consisting of data instructions are processed much like an assembly line. When one part of the processor is done with the instruction, it hands it off to the next part of the processor and starts on the next instruction. For best performance, you want to keep the assembly line of data and instructions moving. To keep the assembly line moving, the processor will attempt to figure out what instructions and data it needs next. If the processor predicts correctly, the processor will maximize its performance. If the processor predicts incorrectly, the processor will have to stop the assembly line and bring in new instructions and data. Fortunately, the processor predicts pretty well. Since RAM is slower than the processor will have to sometimes wait for instructions and data from RAM. The cache is used to store frequently used data and instructions, but it does not always have to grab it from the slower memory. Since the cache is part of the processor, it is typically running much faster than data stored in memory. In addition, processor cache improves speed by fetching data in blocks around the requested data, anticipating that nearby data will likely be needed soon, and storing it in a faster memory for quicker access, and the processor employs prefetching, which is a technique where the processor anticipates what data it will need next and loads it into the cache before it is actually requested. Essentially, the processor cache helps keep the assembly line moving. Today, processor cache is divided into 3 levels: L1, L2, and L3. L1 is the fastest and smallest of the three, while L3 is the largest but slowest of the three. Each processor core will have its own L1 and L2 cache. While the L1 is divided into data instructions cache, L2 and L3 are not. L3 cache is shared across all cores on a die. As you can see, L1 cache is only 64 kilobytes per core, and the L3 cache can be 16 megabytes or larger. Today, most processors are multi-core processors that actually contain multiple processor cores in a single package. Multi-core processors can run multiple sets of instructions at the same time. Sometimes, multi-core processors can have more precise names, such as dual-core processors that combine two processing cores in a single unit, while quad-core has 4 processing cores. Octa-core combines 8 cores. Today, many programs are multi-threaded, which means that the program is divided into multiple sets of instructions that can be executed simultaneously. For example, when you're typing in Microsoft Word, you have one thread that is processing the data that you type into the document. You have another thread that is constantly checking your spelling, and another thread that is formatting your document. Remember, not all programs support multi-cores. While AutoCAD can benefit from multi-core CPUs, it's primarily a single-threaded application, meaning most core tasks rely on a single core's performance rather than leveraging multiple cores. Both Intel and AMD have processors that have built-in graphics processing units or GPUs. Integrated GPUs handles graphics-related data and instructions for processing web pages, streaming high-resolution movies, and streaming and casual gaming. Symmetric processing is the most common form of multiprocessing, whereas a single operating system manages the resources of all processing cores. Programs within the OS can be designed to use multiple processors simultaneously, or multiple programs can be assigned separate processors. Processors in symmetric environments share the same memory bus and other external resources. If you have a system that has multiple physical processor sockets, the processor will need to have the same or compatible steppings. The processor stepping represents the version of iteration a processor goes through. It tracks revisions and improvements made to a CPU's design and manufacturing process, indicating minor or major changes. These changes can be due to manufacturing improvements, bug fixes, or feature additions and removals. Stepping identifiers commonly comprise a letter followed by a number, for example, B2. Mixing processors with different stepping levels can sometimes lead to compatibility issues, especially if the differences are significant. It's generally recommended to use processors with the same stepping level in a multiprocessor system to ensure optimum performance and stability. As a rule of thumb, one stepping difference between two CPUs is generally acceptable. Two steppings is pushing it. Sometimes, software license will be based on one of the following: number of computers running software, number of physical processors, or number of cores. You may need to look at different scenarios where you have to figure out the cost of the hardware combined with the cost of software running on different scenarios to determine the best value. For example, your software may be very expensive based on the number of physical processors. Therefore, you would consider buying a single processor with more cores than having multiple processors. If it's based on the number of cores, you may look at a processor that has lesser number of cores on a single processor. For the various scenarios, it's all about the math. Today, Intel and AMD processors have simultaneously multithreading, or SMT, which allows the processor to act like two logical processors so that it can utilize the processor resources more efficiently and improve performance. It accomplishes this by queuing multiple assembly lines so that if it has to wait for data instructions, it can jump to the other assembly line. Typically, SMT offers 15 to 30% performance improvements. Intel SMT is called hyperthreading. For hyperthreading to be turned on, it must be enabled in the BIOS setup program. The BIOS setup program will be discussed more in future videos within this series. Processors have virtual technology, also called virtualization, which allows you to run multiple virtual machines on the same physical computer. It allows you to run different operating systems which can be isolated on the same physical computer. Each virtual machine would be assigned its own memory space, which are kept isolated from the other memory spaces. Processors have hardware virtualization, which is faster and easier to manage than software virtualization. Intel calls their Intel Virtualization Technology, or VT, and AMD calls their AMD Virtualization, or AMDV. Most virtualization softwares, including VMware EXI and Microsoft Hyper-V, requires hardware virtualization, which is enabled in the BIOS setup program. If you have a virtualization software and you try to create and run a virtual machine, and the virtualization software does not allow you to, you should verify that the virtualization is enabled in the BIOS setup program. Clock speed, also referred to as the frequency, is the speed at which the processor executes an action, such as read a memory address, put a value in a register, or do a single calculation. The clock is used to synchronize the various components in the computer. A computer works by many on-off switches made of nanotransistors. For a transistor to switch from on to off or off to on takes time, although the time is measured in microseconds. Processor transistors can turn between off and on billions of times a second. If a circuit tries to read a signal while it is in transition between on and off, the circuit gets confused. The clock cycle, or tick, indicates when a circuit is supposed to do its next action, so that it does not read a circuit that is in transition from on to off or off to on. You can think of the clock signal as a drum beat or stroke command used on a ship or boat that has multiple rowers. The drum beat or stroke command tells the rowers when to row so that all rowers row together. If they did not, the ship or boat would not go as fast as it could, and conflict can occur as the oars hit other oars. Today, processors perform 4 activities per clock cycle. Clock speed frequency is expressed in hertz, or cycles per second. In 1971, the early Intel processors operated at 740 kilohertz. In 1979, the Intel 8088 processor, which was used in the original IBM PC, operated at 4.77 megahertz. The first 1 gigahertz processor was released in March 2000 by AMD and Intel. Today, processors reach 6.2 gigahertz or higher. The faster the clock speed, the more actions and instructions the processor can execute per second. Looking at the metric table, a 1 MHz processor is performing action a million times per second. A 1 GHz processor is performing actions a billion times per second. The frequency is an easy calculation as it relates to time. Frequency equals 1 over time. For a 4.77 MHz processor, the transistor has to transition in 209.6 nanoseconds. A nanosecond is 1 billionth of a second. For a 1 GHz processor, which would be 1 divided by 1 GHz, which means that the transistor has to transition within 1 nanosecond. For a 6 GHz processor, the transistors would have to transition every 0.17 nanoseconds. Overclocking is running the processor at higher speeds than the one at which the manufacturer rated it. It usually requires more voltage and will generate more heat, which can shorten the life of the CPU. Since it generates more heat, you may need a greater thermal solution to deal with additional heat. Keep in mind that if you increase the processing speed of the processor may not have the ability to keep up and errors may occur. Since you're running the processor faster than the manufacturer rating it, overclocking will usually void the warranty. Instructions and data move along a bus, which is a group of signal lines that transfer electrical signals between different parts of the computer. Usually, each signal line can carry a single bit of data. Most of today's processors use a 3-bus system architecture, which includes the following. The data bus moves the data instructions in and out of the processor, while the address bus specifies the address that the data is going to or from. The control bus is used to send the control signal, such as when to read or write, reset, interrupts, or errors. If your bus has more signal lines, the bus can transfer more bits at a time. A 16-bit bus will transfer 16 bits of data, while a 64-bit data bus can carry 8 bytes or 64 bits of data at once. The address bus specifies the memory address that the data is going to or from. It also specifies how much memory you can access. If you have a higher number of signal lines, you can specify a larger address. For example, early processors can only access 1 megabyte of memory because they only had a 20-bit address bus. A 32-bit address bus can access 4 gigabytes of memory, and a 36-bit address bus can access 64 bits of data. While the 64-bit address bus can access up to 16 exabytes, the amount of RAM will usually be limited by the motherboard. Older legacy processors are 32-bit processors, also known as x86, which refers to the family of instructions ending in 86. While the instructions were created for the 32-bit processor, 64-bit processors can execute the x86 instructions. 32-bit processors only have a 32-bit address bus, which means they can only access 4 gigabytes of memory. 32-bit processors can only transmit 32 bits in parallel because it only has a 32-bit data bus. 32-bit processors' largest registers are 32-bit, which means it can only process 32-bit numbers. It can process larger numbers, but it requires more registers to separate values before storing them, and may take several actions to perform the same action, where a 64-bit processor can do it in one action. 32-bit processors can only run 32-bit programs. It cannot run 64-bit programs. While the PC and server market has largely transitioned to 64-bit processors, 32-bit processors are still used in specific applications and legacy systems, including embedded systems and older software. Newer processors are 64-bit processors, which means that you can execute 8 bytes of data in one instruction cycle instead of the 32-bit processor that can execute 4 bytes of data in one instruction cycle. Since the 64-bit processor is larger, it can hold a much larger array of values compared to the 32-bit processor. The number 64 corresponds to the number of bits that can be processed or sent. The 64-bit processor has the capability to do more work during each instruction cycle if the program takes advantage of those capabilities. For example, if you had to do calculations on numerous 16-bit numbers, you can bring 4 of those into the processor at the same time and perform the calculation on all 4 values during the same clock cycle. 64-bit processors can access 64-bit address, which allows up to 16 million terabytes. 64-bit processors can run 32-bit programs and 64-bit programs. Processors are divided into the set of commands that they execute. One type of processor uses CISC commands, while the other processors uses RISC commands. CISC is short for Complex Instruction Set Computer, which has a single instruction that do all of the loading, evaluating, and storing operations. While it minimizes the number of instructions per program, but increases the number of cycles per instruction. Intel and AMD processors use CISC. RISC is short for Reduced Instruction Set Computer. It is composed of few basic steps for loading, evaluating, and storing operations. While it reduces the cycles per instruction, but requires more instructions per program. Usually RISC is found on smartphones and tablets. Question: which of the following determine the amount of RAM that a processor can access? Answer: the address bus. Question: what is the clock speed of a processor measured in? Answer: hertz. Question: true or false? Multi-core processors are always faster when running software. Answer: false. The program must be written to utilize multi-core processing. Question: you need to order a newer server for specialized application. The vendor licenses with a per socket license fee. Which server would you recommend while maximizing processor power while minimizing license fees? Answer: use a single processor with 8 cores. You'll still need to look at the cost of license and compare the cost of the processor, but most likely you'll save money to use a single processor with 8 cores since you only need to purchase one per socket license for the software. Also, the single processor with 8 cores will give you better performance than the single processor with 8 logical cores, since with hyperthreading that is only 4 cores. Question: you replace the motherboard. While you look at Task Manager, you notice that the processor has 8 cores and 8 logical processors. How do you enable hyperthreading? Answer: you need to enable using the BIOS setup program. When you're done, it will still show 8 cores, but 16 logical processors. Question: you're trying to run Hyper-V, but you cannot create or run any virtual machines. What is most likely the problem? Enable virtualization in the BIOS setup program. For more information about processors, visit these sites. In summary, at the center of the computer is the microprocessor, sometimes referred to as just processor, central processing unit, or CPU. Newer processors are 64-bit processors, which means that they can execute 8 bytes of data in one instruction cycle. Pipelines execute an instruction much like an assembly line. If you have a system that has multiple physical processor sockets, the processor will need to have the same or compatible stepping. Simultaneously multithreading allows processors to act like 2 logical processors so that it can utilize the processor resources more efficiently and improve performance. Virtual technology, or virtualization, allows you to run multiple virtual machines on the same physical computer. Clock speed, also referred to as frequency, is the speed at which the processor executes an action, such as read a memory address, put a value in a register, or do a single calculation. Clock speed frequency is expressed in hertz or cycles per second. Overclocking is running the processor at a higher speed than the one at which the manufacturer rated it. Thank you for watching this video. The next video will be Computer Primary Components Part 2, Installing and Troubleshooting CPUs. If you have not already, subscribe to the Pat Has Your Back channel. Thank you.